This is a short introduction to a straightforward method of assessing project cost uncertainty to set targets and contingencies. I'm going to say a few words about estimates to start us off, because this method is based on the way an estimate is developed. If we remind ourselves how an estimate is evaluated, it might vary in detail, but in broad terms, we will have a work breakdown structure describing what has to be done, a list of materials and equipment to be purchased, and a schedule, even if it's just a list of key dates on a bar chart. We feed in design information about the numbers of items and quantities of materials or labour required, unit rates and durations, and calculate the total cost with a simple arithmetic relationships. The calculations might be made in a spreadsheet or a specialist estimating tool, but it's usually just addition, multiplication, subtraction and division. There's nothing tricky about the calculations. There is a lot of information in most estimates, but it's combined using simple arithmetic. Very often we will need to assess the effect of changes to the estimate. There are many reasons why we might want to vary an estimate: changes to the design, new quotes, rearranging the schedule, value engineering and optimization, anything. My interest in variations to an estimate lies in the fact that if we want to evaluate a variation and we want a quick answer, we don't start from scratch. We just change the inputs, rework the numbers and recalculate the total. And in fact, we often do this using a summary of the estimate. So if we want to know the effect of reducing the size of a project management team by 10%, we can just pull out the total project management staff cost, take 10% of that and get a realistic answer directly. Similarly, if we want to know the impact of the project taking 15% longer than planned, and we can pull out the time-dependent costs, we can assess the impact as being around 15% of that amount. And these approximate methods are perfectly good for normal decision making. To do this, we only need a summary of the estimate. It might take different forms depending on where the uncertainty lies and what type of project it is, but a common summary is based on the separate types of work or disciplines and the different types of costs, such as labour, materials, equipment, and so on. After an estimate has been assembled, variations can be assessed without going back into the detail. None of this requires complicated calculations. There may be a lot of data, but the underlying calculations are simple. We can exploit the same approach to understand the effect of risk on a cost estimate. I'm going to illustrate how the approach often used for what-if analysis can provide a framework for straightforward risk modelling. Leaving aside parametric methods, there are three approaches in general use for assessing project cost contingencies. Risks have been described as events that either happen or not for a long time. This is the approach in which we multiply probabilities and impacts together and add up the results. Another long-standing practice is for the estimator to include allowances line by line in the estimate to cover risk. And the third way, which has only become prominent relatively recently, is called risk factor modelling. I'll get onto that in a minute. Risk event modelling is a method that came into general use before we had computers to help us do anything better. Some sources of uncertainty suit being represented as events. For instance, if the design assumptions on which your estimate is based might change, say there's a 1 in 10 chance, and if they do, extra costs will be incurred, a risk event model makes sense. In this case, there's a 90% chance there'll be no impact from the risk and a 10% chance of some additional cost, which could be evaluated and built into a model. But a lot of uncertainties aren't like that. Think about the productivity estimates you've used to work out how much effort will be required to complete a task and how long the work will take. The productivity might be lower, so that you need more effort, and this will increase costs. It's not likely to be an exact amount lower than you've assumed, though. This is the sort of uncertainty where the actual value could be somewhere in a range either side of the value assumed in the estimate. The uncertainty is better described by a distribution than an event. The same goes for many of the reasons why an estimate might not turn out exactly as you've assumed. Take the cost per month of project overheads. It could be a bit lower or a bit higher than you've assumed, within a range. Neither of these cases is well represented by an event model. There are other problems with a risk event modelling approach. There's a danger of double counting, especially where schedule delays can have cost impacts. If there are two delay risks, and they'll definitely happen at different times in the project, so they won't overlap, we might be able to treat them as independent events and add up their impacts. However, if there's a chance that the delays could overlap, the total impact will usually be less than the sum of the two separate risks, and some extra analysis would be required to figure out how much it could be. The other challenge with risk event-based models is interactions between uncertainties. If we have a risk of a delay, we can calculate its impact in terms of the delay duration and the running rate of the overheads. If we have separately a risk of needing more people on the project management team, perhaps because of unexpected complexity, we can calculate its impact in terms of the team size increase, the overall project duration, and the baseline running rate of overheads. However, if both risks affect the project, both of them happen, each one will change the parameters used to calculate the impact of the other one. Where there are several risks and lots of possible interactions, it's very difficult to work out what the net effect will be. Risk event-based models, often constructed on the project risk register, are awkward to use and they're often unrealistic. Line item risk models usually apply a distribution of costs to each line in a summary of the estimate. This method evolved from the way estimators used to make allowances for risk as fixed amounts line by line, and some still do. Instead of putting a fixed allowance against each line, they might now put a distribution of values against each line. It looks simple, but soon becomes either unrealistic or very complicated. The biggest problem is that line items are often correlated in complicated ways, and this is difficult to understand, let alone to model. Say these two lines are both affected by uncertainty about the amount of complexity in the design, which is not yet completed. If it's very complex, they'll both tend to grow, and if it's simpler than we expected, savings might be possible in both costs. The amount of correlation this will cause is difficult to assess, and even more difficult to explain to other people. It gets worse though. Imagine that one of those costs is also linked to another one, because they depend on how good a development team we will have and how productive they will be. Assessing the correlation between the costs uncertainties is now even harder, because the first two are correlated one way, the second two are correlated a different way, and without getting into the statistics, this actually means that the first and the third will be correlated to some extent. With the correlations overlapping, they interact with one another, and this interaction should really be included in the model if that's what we really believe, but there's no practical way to analyse this with a project team and get realistic assessments of correlation from them that can be linked back to their knowledge of the project. There are other problems with this sort of modelling as well. What usually happens is that correlations become fudge factors used to adjust the results till the answer looks right. There's no problem with adjusting a model to reconcile it with other sources of information about the project, such as experience and judgment. But if you can't explain why a certain number makes sense, it becomes little more than a way to dress up that judgment and make it look more impressive by linking it to a model. Not allowing for interactions such as that between the cost of overheads per month and the duration of the project is a problem with line item ranging, just as it was with risk event-based models. In some very simple situations, or as a small part of a larger task, a model of this sort might be useful, but it's not a good choice as a primary approach to assessing project cost uncertainty. Now I want to go back to the original estimate and think about what a computer can do for us over and above basic arithmetic. Imagine that there is a factor that affects the cost and is uncertain, perhaps the project duration or the size of a software system that isn't clear at the time the estimate's being prepared. We can use the same approach as we do for quick what-if analysis to understand the effect of the uncertainty in this factor on the total cost. We can choose a value from the distribution and use it to vary the estimate just as we did for what-if analysis. Change the input, rework the estimate, recalculate the total. One of the values for the uncertain cost driver will produce one value for the total cost. We can sample the uncertain input repeatedly and calculate the effect on the total repeatedly. By the time we have sampled lots of values from the input distribution, we will have built up a simulated distribution of the total cost. And of course, there won't usually be just one uncertain cost driver in a project. There will usually be several. They might include the duration, the scale or quantity of the work, rates for labour and materials, workforce productivity, and others. If we go through this process many times, with all the uncertain inputs being sampled at the same time, we will get a simulated distribution of the combined effect of all those uncertain cost drivers on the total cost. As with a quick what-if analysis, we don't need to use a large complicated estimate to carry out this sort of analysis. We can do it with a summary of the estimate, so long as the summary allows us to apply the cost drivers to the parts of the costs they will affect. Things like material costs, labour costs, overheads, major lump sum purchases, and so on. And all of this can be carried out in a model built in Excel using something like the at-risk add-in. This is an illustration of parts of a risk factor model for a small IT project. The overhead costs are subject to uncertainty about the running rate of the cost in dollars per month and about the duration. The duration itself is subject to uncertainty about the scale of the software and about the productivity of the team developing it. Uncertainty about the scale of the job and the team productivity also affect the total spend on professional services, along with the uncertainty about the market rate for professional services. And then it may be that the cost of installed licenses will be subject to uncertainty about the number of end users and the market rate for licenses, as well as a design decision, possibly a choice of operating system or some other feature of the system. That design decision, as it is shown here, would be an event in reality, and so it would be modelled as an event in the model. It's either one thing or the other, not somewhere in a range. The uncertainty about rates, scale, and duration is all variation within a range, not events, and it's important to keep the two distinct. Here is a real example of a model implementing what was shown in the preceding figures. On the left, we have the base estimate, just 3 items in this very simple case, and on the right we have 7 uncertainties, risk factors. 6 of them are defined by optimistic, likely, and pessimistic forecasts, and the distributions in these brown cells on the right, which we can see one of here, use those to define a probability distribution function, a special at-risk function, which means that when the simulation is run, this cell will take on a value between the optimistic value and the pessimistic value, and it'll be most likely to fall near the most likely value. But it could be anywhere in that range with decreasing likelihood as you get towards the extremes. It's a very simple shape we're using here, triangular shape. It turns out that doesn't really make much difference at all. The design decision variable, that's only going to take on one of two values. Either the costs will be as assumed, so the factor is 100%, or the costs will be 50% higher. And you'll see that if I press the F9 key, these variables all move, and the continuous variables, the 6 on the right, take on a value somewhere in the range between their optimistic and pessimistic value, and they tend to fall near their most likely value. The design decision variable only takes on a value of 100% or 150%, and it will work out on average that 4 times out of 5 it'll be 100%, and 1 time out of 5 it'll be 150%. Those factors are used here to simulate the total cost. So if we look at the overheads, this value here is calculated from the base overhead cost, that value in B4, times the overhead rate factor, that's this one here, and the duration factor, which is this one here. The duration factor, you might remember from the previous slides, is calculated by the combination of the uncertainty in the software scale and in the team productivity. The arrows aren't strictly part of the model, but they just help to illustrate here how it's put together. So these two factors drive this cost, these three factors drive this cost, and these three factors here, which includes this design decision discrete variable here, drive this cost here. The total is calculated here, and that's recorded during a simulation every time the model is iterated. These distributions are sampled. These values are calculated using the new values from the distributions and the base cost here. The total is calculated, and that's recorded. Now if I run the simulation, I'm going to run it for 10,000 iterations, you'll see the range of values that those risk factors generate in the total cost. So remember, we're starting with a base estimate of $475,000, and occasionally, if all those factors move in the right direction, it's coming down to around $400,000. And also, occasionally, if they all go in the wrong direction at the same time, it's getting up around $750,000. The likelihood of making that $475,000 initial estimate is looking like about 1 in 20, 5%. The most likely outcome appears to be around $550,000, and it wouldn't be surprising if we got a value around $650,000. Now sometimes it's easier to decide how much contingency you want to add on to that base cost there to give yourself a reasonable target by looking at the cumulative distribution, and this shows the risk of exceeding any particular value in this range. So if you want a target that has about a 1 in 10 chance of being exceeded, then you would be aiming for 640,000 roughly. If you wanted to be a bit more adventurous and wanted a target that had about a 1 in 5 chance of being exceeded, you could get away with, say, $615,000. But if anybody was trying to do this for the initial estimate with no contingency, they'd be more than likely, a lot more than likely, going to exceed their target. There's a lot of information you can get out of this analysis, and one of the very useful pieces of information you can get is to look at the relationship between the uncertainty in the inputs, that's the uncertainty factors here, or risk factors, and the uncertainty in the output. And this shows the extent to which uncertainty in the inputs is driving the spread, that range from 400,000 to $750,000 in the outputs. And you'll see that these top three factors in particular are having a significant effect. So uncertainty in team productivity, software scale, and the design decision are really serious. Uncertainty in professional services rates is not trivial either. But these three here, uncertainty in the number of users, the overhead rates, and the market rate for licenses, is not really having very much effect on the spread in the outcomes. So if you needed a more precise answer, a more precise forecast of the total cost in order to make a business decision, these 3 or 4 items at the top are the ones that you would want to work on in order to narrow that range and give yourself a more confident estimate in the outcome. A straightforward model can capture the uncertainty affecting a project estimate. It can give us guidance on where to set realistic targets and contingencies, which risk factors cause the most spread in the range of possible outcomes, and which contribute most to the contingency. And it can give us a documented explanation of the rationale for the inputs and the ranges used. Finally, if we use a model such as this to understand the risks affecting a project's cost, we can test and strengthen our judgment about targets, contingencies, and sensitivities so that what we believe about the project is supported by an informative model, and both the model and our beliefs are consistent with the real nature of the project.